Well, good afternoon, everyone. My name is Alan Rossiter, and I'm with the University of Houston, and I'm speaking on behalf of the Texas Industrial Energy Efficiency Program, and I welcome you to our Spring Energy Forum. TIEEP is a program of SECO, the Texas State Energy Conservation Office, and it is administered by the University of Houston through Energy. For many years, the Spring Energy Forum has been run in collaboration with the South Texas section of the American Institute of Chemical Engineers, or STS-AICHE, and it has been co-located with their April dinner meeting. Due to the current restrictions on in-person meetings, the dinner has been canceled, and we decided therefore to run the Energy Forum as a webinar. However, we'd still like to recognize our partnership with STS-AICHE, and we have carried over several elements from the dinner meeting into this webinar. For example, STS-AICHE has two sponsors for the meeting, SECO and TLV, and we'd like to thank them for their support. The theme of the Energy Forum is Plant Resiliency, Lessons from Harvey. When we decided on this theme, we planned to present a diverse series of talks on how Hurricane Harvey has tested the resiliency of the Texas Gulf Coast and what we have learned from this, with a focus on industrial performance and especially energy efficiency. Well, in the immortal words of the great Scottish poet Robbie Burns, the best laid schemes of mice and men gang after gley. We lined up some excellent speakers, but about a month ago, the two who were going to provide an industrial perspective both canceled. After unsuccessful attempts to find replacements, I agreed to fill the slot that they had vacated. I'm with the University of Houston now, but most of my career has been in industry, so this isn't too much of a stretch. I would also note that about 10 minutes ago, one of our other speakers announced that he was not going to be able to join us, and he is Commander Joe Leonard from the Coast Guard, now retired, but he is currently working as an emergency management consultant, and he has an emergency to deal with. So he may be able to join us at the end of the webinar, but as of this point in time, he is not going to be with us. However, we do still have something of an all-star cast remaining. Kenny Mercado is Senior Vice President for Electrical Operations and Technology at Centerpoint Energy, where Kenny is a 34-year industry veteran. And our other speaker really comes to us courtesy of the South Texas section AICHE. Their designated dinner speaker for the dinner that has been canceled is Chris Knoop. He is CEO of Carbon Sequestration, Inc. And as I say, he was slated to be the after-dinner speaker. His topic, a new approach to carbon sequestration, is not directly related to the Energy Forum, but it is still highly relevant to all of us who are engaged in energy management and greenhouse gas abatement. And I'm sure you'll find it both interesting and instructive. As you will have gathered from what I've said, we will have to do a bit of juggling on the sequence of the presentations, but we'll work through that as we go forward. For now, though, we do have a special guest, a presentation or a quick word from our sponsor. So Steve Garrett from TLV, would you like to give a quick word for us?
Yes, absolutely, Alan. Thank you so much for this opportunity. Of course, TLV is honored to always participate in any event sponsored by the Energy Forum or the AICHE. And again, for this event, we're grateful for the opportunity to be a part of it. I thought I would tell you a little bit about me and our company. My name is Steve Garrett. I am the Gulf Coast Operations Manager for Texas, part of Louisiana, Arkansas, and also New Mexico. TLV Corporation is a company that is divided into three parts. It's a manufacturer that has an engineering arm and, of course, a distribution arm. Our business is about ridding steam and air process systems of condensate. And we do that by means of manufacturing steam traps, pumps, separators, air handling equipment, different products used in ridding steam systems of water, of condensate. These products are used in order to drain reboilers and turbines and waste heat boilers that produce so much wet, entrained condensate into the steam systems. We do that with products that we're known for, the free float trap, again, and separators who have a 99.8% capability to reduce the wetness in steam. So we're very excited about that and the opportunities that we have in the Gulf Coast. We work a lot with EPCs in designing steam systems. I'm very fortunate to be an SME with several of the larger refining operations here in Texas. We have a training center in the energy corridor right off of the Katy Freeway, where we do a lot of training for engineers, maintenance, and operations folks in the various different industries: refining, chemicals, food and beverage, pulp and paper. Anywhere there's a boiler or a compressor. The engineering part of our company does a lot of work around walk-through systems. We'll go into a plant and take a look at a particular unit, walk through it, and assess it. TLB is also the only company in the world that I'm aware of that has the ability to do risk mitigation work around steam. We're currently working with several of our partners, refining partners in that effort. And in light of all of the regulations around flares and such as that, it's come in very handy. We do steam balance work from a mechanical standpoint, where we go out into the plants and look at each piece of equipment and how that relates back to the boiler. We also have a distribution arm to our company, and that in Texas, in those areas that I just mentioned, is Rawson. You may be familiar with Rawson, as they are an old-time distributor in the Texas and Louisiana markets. TLB's goal is simple. We want to get condensate out of steam systems. We want to help plants be safe first. We want that equipment to be reliable and available. We want to be certain that the processes are run as efficiently as possible. And of course, we're concerned with the environmental effects that may be caused by poor steam systems. Again, thank you very much, Alan, for this opportunity, and of course to showcase TLB a little bit. And I'm certainly looking forward to the speakers this afternoon. Thank you again.
Thanks very much, Steve. All right, our other sponsor through STSAICHE is TRACECO. TRACECO is a company that is engaged in gamma ray scanning technology to generate insights, especially in distillation columns and their performance and troubleshooting. Insight through innovation is their motto, and you can see more details at www.traceco.com or contact them at traceco@traceco.com. All right, I'd like to spend just a couple of moments giving you a quick orientation on Zoom for anyone who is new to this system. If you move your cursor to the bottom of your screen, if you've not already found this, there is this sort of black bar that you see here. And this allows you to pull up a menu of different items. And so you'll see on the extreme left here, there's an opportunity to mute yourself or to start and stop the video, assuming these have not been frozen by the host. But the things I mostly wanted to focus on were the participant list, and you can see that icon near the middle of the screen at the top. And if you click on that, you'll see who else is on the Zoom meeting. And then further over to your right, you will see the chat icon. So if you need to communicate individually by text messages while the meeting is in progress, you can either chat to individuals or to everyone by selecting from the drop-down menu. And you're going to need that in a moment for the next item I want to talk about, which is this, certificates of participation. we are offering those specifically for engineers, because many people require professional development hours as part of their engineering registration. And for those of you who require a certificate of participation as a Texas engineer, during this webinar, please send a chat message using that chat feature that I just showed you to Lee Lopez, and you should see her identified. Lee, actually, can you raise your hand on the participant list? Okay, so Lee has her hand raised if you look at the participant list. So she will be handling preparation of Texas PDH certificates for those who wish to have those. So to get your Texas PDH certificate, you need to chat your name and your email address to Lee, and she will prepare the certificates and send them to that email address. In addition, we do have a bonus here from a colleague of mine. LG Environmental Engineering is an authorized Florida Board of Professional Engineers provider of technical continuing education. And they are pleased to offer continuing education credits for the forum today. Their certificates are accepted by the Florida Board of Professional Engineers and also the majority of US boards as well, and Canadian. In order to get your PDH certificate for states other than Texas, you will need to send additional information, and I'm going to put this information in the chat feature if I can get it to work. So basically, again, if you can send your information, and I can't send it right now, I'll put this in the chat as well. You'll need to send your request, including all this additional information. This is your name, certificate number from your license, the licensing entity, state or country, and send that to Lee Lopez, but here is her email address, since that's rather more complicated information. And in the subject line, you need to put Texas Spring Forum PDU. All right, so if you need a PDH certificate for a state other than Texas, please send your information, that additional information, to Lee by email. And I will put that request in the chat box in a moment. Okay, I'll have to come back to that. One other item to mention for you here, we will have Q&A on this webinar, question and answer. If you have a question to ask, please send it to me, again, using the chat feature. So send your message to me using the chat feature, and we will then take Q&A after each of the presentations. So during a presentation, if you have questions, please put them into the chat box and send them to me, and I will review them, and we will ask questions at the end of each of the individual presentations. Okay, so as I mentioned, the first presentation is one that I'm actually providing myself. I'm Alan Rossiter, Executive Director for External Relations and Educational Program Development for UH Energy at the University of Houston. And I've been at the university just over a year. Before that, I worked for 2 major chemical companies, and I also spent a substantial part of my career in consulting, both with a small firm and then as an independent consultant on my own. My academic training, bachelor's, master's, and doctoral degrees are from the University of Cambridge in chemical engineering, and I am a licensed professional engineer here in Texas and also a fellow of the American Institute of Chemical Engineers. And I will be talking about Harvey and the beauty of the steady state. This Energy Forum is organized by the Texas Industrial Energy Efficiency Program. And you may wonder what Hurricane Harvey has to do with energy efficiency. Well, I'm sure there are a lot of different answers to that question, but the point that I mostly want to make is this. Chemical plants, oil refineries, all run best when they run under steady conditions. That means better production, better quality, and yes, also better energy efficiency. Any sort of disturbance or disruption will tend to make all of those parameters worse. And Harvey was one big disruption. And we'll talk about some of the implications of that during the course of this presentation. But for the moment, I think all of us who live in the Houston area, or certainly lived here during that time, have a Harvey story. And I'd like to tell you a little bit about mine. I was actually out of the country when the hurricane hit. Of course, I knew it was on the way because of the weather reports, but I didn't have any concept of the real scale or the impact that it was going to have. What really got my attention, though, was when I received a photograph in my inbox. Yes, that is the breakfast room in my house with 18 inches of water in it. And yes, that is a bicycle, which proves this must be the Rossiter residence. As it happens, that particular bike is my wife's, not mine, but you get the general idea. Anyway, once I had taken in what that picture was showing me and recovered from the impact, two thoughts crossed my mind. First of all, my wife has been wanting to remodel for a number of years, and now she's going to have her opportunity. And number two, thank goodness we've got insurance. Well, I was out of town, as I said, in fact, out of the country, and I needed to get back home. So I tried to get the first available flight, though it took several days because the airport was, of course, closed after the hurricane. And when I did get back, I was actually on one of the first flights that was able to fly into Intercontinental Airport. As we were approaching the airport, it was a rather surreal experience because when I looked down, there were lakes where there weren't supposed to be lakes. And I also noticed a cluster of houses that seemed to be sitting at the side of canals. And from up in the air, it looked like they may have been transported from Venice, and it was a rather pretty little picture. But I'm sure if you lived down there, it was anything but pretty because those weren't canals. They were flooded streets. When I got back to Bel Air, where I live, the sight was also quite stark, quite striking. Outside virtually every house along my street, there were piles of debris. Looked a bit like a war zone. And Bel Air itself was one of the worst hit places. About 40% of the houses in the city got fairly severe damage. Our area in Bel Air, our subdivision, if you want to call it that, was hit far worse than that. It was much more than 40%. So it was not a pretty sight. But of course, the damage was not limited to our small part of the greater Houston area. The chemical plants, the refineries were hit pretty hard. The total cost of Hurricane Harvey has been estimated at about $125 billion. And looking at that chemical sector, the petrochemicals in particular, this little table shows you the impact that the hurricane had on plant capacity due to shutdowns. And you'll see there that if you look at some of the major petrochemicals, roughly 23% of the propylene production in the US was shut down as a result of the hurricane, rising to nearly 37% of the ethylene capacity. So those were huge hits on petrochemical operations throughout the US, but especially here in the Houston area and along the Gulf Coast. So, as I've said, steady state is good. How do we come to that conclusion? Well, I think this one equation really gives a big hint. And what this tells us is simply the definition for energy intensity, which is the amount of energy that you consume divided by your production. How much energy per unit of production. And so energy intensity rises, which really means efficiency falls when energy consumption increases or production decreases. And as we'll see in the next few slides, this almost always happens when your operations are unstable or your conditions are in some way abnormal. We started this presentation with my Harvey story, and then we got technical with the definition of energy intensity. I'd like now to lay out the agenda for the rest of this talk, and we'll start with some examples, some detailed examples of how energy intensity is affected by disturbances in the plant. First of all, looking at summer rainstorms as an example, and then talking about some throughput cut situations and the impact that those have. We'll then move on to some other situations more generally, and then move on to see how this applies in the case of Hurricane Harvey and other major natural disturbances that might occur. And then we'll wrap up with a brief discussion of some ways to mitigate these effects and have less of an impact on energy intensity. As we go through these examples, you'll see this little table come up a number of times. And here we're looking at the three parameters we talked about in our equation. First of all, the EC, which is energy consumption. Secondly is production rate, P. And then the third one, EI, is the energy intensity. And we'll be looking at how each of these changes in each particular example that we look at. The red obviously means a bad change. So energy consumption going up is adverse. Production going up, on the other hand, is a good thing, and energy intensity going down is also a good thing, so those are shown as green. So, moving on with our agenda, we'll turn to the detailed examples that I mentioned. And the first of these is the summer rainstorm. The specific example I'd like to talk about is distillation column performance and how summer rainfalls can affect that. We have people from many different disciplines in this webinar, so I must briefly explain that distillation is the most common method for taking a liquid stream that contains a mixture of chemical components and separating those components into separate streams. It does the separation by boiling the liquid at the bottom of the distillation column. The components that boil at the highest temperature remain as liquids and leave at the bottom of the column. Those that boil at the lowest temperatures go up the column as vapors, and they are condensed after they leave the top of the column. The column is hottest and the pressure is highest at the bottom, and the temperature and pressure are both lowest at the top. And the compositions of the liquid and vapor inside the column also change as you go from the bottom to the top. Now, let's consider what happens when there is a heavy rainstorm. In many distillation columns, the overhead equipment is not insulated, so the pipes and equipment are cooled rapidly by the rain. This increases the rate of condensing, which causes the pressure at the top of the column to fall. This, in turn, causes more material to vaporize inside the column and go to the top. This includes some of the material that is supposed to go to the bottom. Consequently, the overhead composition changes and it can go out of specification or off spec, and it may take many hours to get it back on spec. This often means that we have to reprocess the overhead product, in other words, distill it again to get it on spec. And then just to summarize this, when we have our rainstorm, we get an uncontrolled increase in the condenser duty. The pressure at the top of the column decreases rapidly. The liquid on the trays vaporizes more than it normally would, and this additional vapor goes to the reflux drum, and the composition of that vapor is not correct. It contains more of the heavier materials than we want in the distillate. So these heavy ends contaminate the distilled product, and so we are left with an off-spec material, out of specification, and this then has to be reprocessed. So what this means is that in order to get back to the composition that we wanted for our overhead material, we basically have to distill it a second time. We have to reprocess it. So the effect, if we go to this table that I talked about, is that the energy consumption goes up because we're having to distill this material twice over. Moreover, our production has gone down because time has been effectively wasted distilling this the first time. And so the overall effect is a double whammy as far as energy intensity is concerned: more energy consumption, over a longer period of time, meaning that production per unit time has gone down, and so the energy intensity is significantly increased. All right, let's turn now to our second example, which is throughput cuts, or ways that we reduce the production in our plant by changing flow rate. And I'd like to focus on centrifugal pumps, which are one of the most common pieces of equipment that you'll find in most refineries and chemical plants. And specifically, I'd like to look at 3 different ways of controlling centrifugal pumps, which have different impacts on the energy intensity that results from flow reductions. The first type of control I'd like to talk about is generally called bypass control, although I personally prefer the term spillback control or even recycle control because I think it actually gives a better concept of what's really going on here. And the idea is this: you have a certain feed stream that you're passing through your pump. It comes out on the discharge side, and you take a portion of that flow to the downstream user of that stream. But the other portion you simply return back to the suction side of the pump through a spillback line. Now, many companies or many consumers like this design, this configuration, because it actually can give you a very stable and steady flow to the user. However, it does have significant disadvantages, as we'll talk about later. Another thing I should comment is that there are actually a number of different variations on this configuration. One of the most common I've seen is that I'm showing here that we take the spillback from the discharge side of the pump and return it directly to the suction line. But in many cases, the feed stream to the pump is coming from a feed tank or a surge tank, and the spillback line can go back into that tank. And that does have advantages. Most importantly, it provides additional stability to the flow. Well, here is a variant of the spillback or bypass control. We have now added a cooler on the spillback line. This is needed because when we pump a liquid, its temperature rises, and if the spillback becomes very large, that could result in overheating of the pump. Let's now look at the material balance here. We are trying to deliver a quantity of flow F to the consumer on the right-hand side of the diagram. On the left-hand side, we must provide that same quantity of feed, big F, on the extreme left-hand side of the pump. We're controlling the flow by adjusting the spillback flow, little f, and that spillback mixes with the incoming feed upstream of the pump to give a combined flow through the pump of big F plus little f. And when we look at this diagram, the flow little f simply circulates around and around. It does not contribute to the net flow through the process. And so let's suppose that we want to reduce the flow, big F, going to the downstream consumer. Well, we do that by opening the spillback valve, which means that little f must increase. Now, there's virtually no change in pressure at either the suction or the discharge side of the pump, and the pump speed is constant, so the flow through the pump, which is big F plus little f, also stays the same. Any decrease in big F must be equal to the increase in little f. Consequently, the power requirement or the energy consumption within the system remains the same. So if we look at our equation for energy intensity, we see that the energy consumption, EC, could go up or down by very small amounts, but it's essentially constant. And the production rate, which corresponds to the flow through the system, big F, goes down. So the effect is that energy intensity goes up. Well, now I'd like to show you a couple of other control mechanisms for pumps, flow control mechanisms. And the first one is what is called throttle control. And here we put a throttle valve on the discharge side of the pump in the discharge line. And as we close that control valve, so we throttle the flow goes down. And there will generally, when we do that, be a reduction in the pump power requirement. However, that reduction, the percentage reduction in the pump power, is almost always a smaller percentage than the reduction in flow rate and the corresponding reduction in plant production. So the net effect, the energy consumption goes down, production or flow rate goes down, and the energy intensity goes up. This is, however, better than the situation with the bypass control or spillback control, because we do at least get some reduction in energy consumption. The third example that we have is speed control, and this is usually accomplished with a variable frequency drive in the case of electric motors. Generally, an electric motor will run at constant speed, and so the pump speed will be also running at constant rate, constant pump speed, and so we have to use valves to control the flow. When we use a variable frequency drive, we can actually reduce the pump speed in order to reduce the throughput or the flow rate. And that then means that, yes, once again, energy consumption goes down as flow rate or production rate goes down, but in some cases, the energy intensity also goes down. In other words, the percentage reduction in energy consumption may, in some cases, be larger than the percentage reduction in flow or production. The example I showed you earlier with the bypass control or spillback control was taken from an actual energy assessment that was carried out a few years ago. The recommendation from that study was to add a throttle valve on the line to the downstream user of that material. And this then allowed a significant reduction in the flow going through the spillback line. And the savings were in the order of $150,000 a year, which was quite significant. You still need to have the spillback line available, however, because this is a mechanism for ensuring that the pump always has at least its minimum flow requirement and that it doesn't overheat. As I mentioned earlier on, that is a significant requirement in this situation. And this also raises a very important point. Whenever you try to change control systems, it's very important that you consider the safety implications and reliability implications of any changes that you make. Well, I'd like to turn now to talk about some other situations where we see significant increases in energy intensity due to changes in operating conditions. And I think the most significant example is shutdown and restarting of plants. While a plant is actually fully shut down, it's offline, there is no production, but even in that situation, there is always some amount of energy being consumed or wasted within the plant. So in that situation, we have our denominator going to zero while there is a finite numerator. So of course, at that in that particular period of time, the energy intensity is actually infinite. During the period when you're shutting down the plant and subsequently restarting it, well, that can take several days in some cases, but during that time we are consuming a considerable amount of energy. For example, during the shutdown period, you may be cooling down equipment in a controlled manner, and then restart, you may be reheating furnaces and other equipment, for example, using energy while you're actually making very little usable product. And you may also end up with off-spec product, as we discussed in an earlier example. This then has to be stored for subsequent reprocessing. And so the result is, even though your overall energy consumption may be less than it would be during normal operations, your net production is way down, and the energy intensity may not actually be infinite, but it's certainly much higher than normal. And I'd like now to talk about just a couple of other cases. So one situation is what you might call a partial shutdown, or often called a squat. And this is commonly used for maintenance activities or to recover from major plant upsets. And in this mode, certain pieces of equipment within a plant will be shut down. Other pieces of equipment will be in a standby mode, so they can be run at low load and put back into full production quickly while the rest of the plant runs. And so overall, you have a situation here where there's obviously some instability in the operation, but also you are producing significantly less product than you normally would from your plant. And the overall effect is an adverse impact on energy intensity. There are also many plants that make a multitude of different products or different grades of the same product. For example, polyethylene, there are many different grades of polyethylene. And whenever you change from one grade to another or one product to another, you will have to do some or all of the things that I list on the slide here. You may have to stop or start pieces of equipment, or maybe the whole plant in its entirety. You may have to change feedstocks or adjust temperatures and pressures and flow rates. And all of these will lead to some disruption to the operation. And as we've seen from previous discussions, this will also lead to an adverse impact on energy intensity. Well, how does all of this apply to Hurricane Harvey? I think it's fairly clear that pretty much everything we've discussed does have an impact in situations like hurricanes and other major disturbances from natural causes. For example, we talked about rainstorms and their impact earlier on. Clearly, when a hurricane comes in, you get rain. You will also have to stop equipment or put equipment in standby mode. But typically with a hurricane, most plants will end up being shut down to protect them and to protect operators. And there will then be an extended period being offline and then restarting. And as we saw from our discussion of plant shutdowns, these activities all lead to an adverse impact on energy intensity. And then even when you come to the final startup of your plant, with a hurricane like Harvey, there is some disruption to the surrounding society, the surrounding infrastructure, and this can result in cuts in your throughput or instability of operation because of problems in the supply chain. And so this also will have a significantly adverse effect on energy intensity and energy efficiency. Well, what can we do to mitigate against these problems? Well, obviously, it's a whole different story dealing with a small disturbance in flow rate or composition in the normal operation of a plant and dealing with a hurricane, very different situations. And so not everything that I list on this page is ultimately going to be useful to you in a hurricane, but it will tend to be helpful in general in improving the resiliency of plant operations. And there are a number of different areas to look at. We can consider the design of our plant, we look at operation, and then also we need to consider external issues outside of your battery limits and the overall infrastructure and environment in which you're operating. So on the design side, the better insulated equipment is, the more resilient it is against fluctuations in external temperatures and rainstorms, as we saw in the example of the distillation column earlier on. Surge capacity within surge tanks, feed drums, product drums, and so on can help to deal with changes in flow rate and composition. And there are ways that control systems can be improved also to manage disturbances. From the operational side, we talked about plants where we change grades or products, and the less often we make those changes, the less disturbance there is. And so if you can go for longer runs with each product or each grade and fewer transitions between them, so you will tend to improve the energy intensity of your process. Also, when it comes to shutting down and starting up processes, there are often steps included in those procedures that are actually unnecessary or can be shortened. And if you can make the startup and shut down activities quicker, then in general you'll have shorter unstable times, and therefore you will improve your energy intensity. Having said that, we have to be very careful with changing operating procedures, because once again, we do have to be very conscious of process safety and equipment integrity, and be very careful not to go outside the safe operating envelope of your process. And finally, something that most of us as engineers typically are blindsided by, we're not only dealing with our own process, we have to consider the surrounding infrastructure and supply chain, and the resiliency of that whole structure is very crucial, especially in situations like hurricanes, where the whole of a region is going to be affected by the disturbance. And then effective emergency management within the emergency situation, like a hurricane. The better that emergency management and the quicker things can be brought back on stream outside of your battery limit, the less your downtime is going to be. And that really is the subject of the next talk that we're going to have. Well, that brings me to the end of what I wanted to say. I do list here some references. The distillation material that I talked about earlier comes from my colleague Charles Herzog. The data on the impact of Hurricane Harvey came from the article listed there by Laura Cassidy. And also I do have an article in press with chemical processing, which is due to come out in June. And so with that, I will end, and happy to take your questions. Okay, so I have received a couple of questions. If anyone else would like to send me a question, please put it in the chat and send it specifically to me, Alan Rossiter. So just one moment here. The two questions that I have so far, have you ever applied energy intensity as a metric to improve energy efficiency in operations? And the short answer would be yes. Very often I have seen energy intensity, the amount of energy consumed per unit of production used within various energy management programs as a mechanism for tracking performance and driving efficiency by identifying the conditions that improve energy intensity. So yes, and it's also used as a design parameter too in many cases. The other question that I've seen thus far was related to throttling. And the question was, how can you be saving energy when you throttle the discharge of a pump? And I guess the short answer is you don't really save energy. What you do, though, is that you do reduce the energy consumption of the pump, typically, because the flow rate goes down. And the biggest contributor to the energy required in pumping is related to flow. What you also do is you push the back pressure up on the pump, and that obviously tends to increase energy. And there are one or two other factors like pump efficiency that come into play as well. But the overall effect in most cases when you reduce the flow by throttling, at least a relatively small amount of throttling, is that you reduce the overall energy consumption by the pump. So I'm looking to see if there are any more questions here. And you may continue to send questions if you have any. But what I will do for the moment is just to roll into, first of all, just a reminder about the certificates of participation. If you have a need for a Texas certificate, please send a text message to Lee Lopez with your name and the email address. And I also put a message into the chat system for everyone. If you want an out-of-state certificate, there are some additional requirements, and you'll need to send an email giving additional information to Lee at her email address. And as I said, also for questions, Q&A, if you have any questions, either from the presentation you just heard or from the next couple, please let me know through the chat system. All right, as I mentioned at the start of the webinar, we were expecting Commander Joe Leonard to be joining us at this point. Unfortunately, he is an emergency management consultant, and unfortunately he is dealing with emergencies, and given what's going on at the moment around us, that's not really surprising. He said he would try to join us at the end of the session, at the end of the webinar, but he did not think he would be able to. So if he does come in later, we will introduce him to you and get him to at least give some of his talk. But for the moment, we just wish him well with all his work in managing the emergency in which we currently share. I will, however, show you a few of his slides. There are a couple of things here that I think you will find interesting, and there are also a couple of videos that are included, so they won't require much explanation. But those of you who were listening to my Harvey story at the beginning of the presentation I gave will recollect that I talked about houses that looked as if they were standing on the side of canals as I was flying into Intercontinental Airport after Hurricane Harvey. And I happened to notice when I was looking through Commander Leonard's material that he actually had a picture of exactly those houses, which unfortunately I was not able to take while I was flying in. However, let's just move forward on these slides, and I'll see if I can show you his videos. except the slides are stuck. So I'm going to have to come out of this for a moment. Oh, here we go. Looks like I'm going to have to come out of this for a moment to advance the slides. All right, so this was just listing severe weather events. But now we come to, I think,
Harvey was different because it challenged us in every way possible. Our major facilities in the storm-impacted areas were essentially isolated because of floodwaters. Coast Guard men and women across our service and at every level displayed remarkable initiative and innovation, overcoming many, many obstacles.
We were able to get in that morning prior to sunrise, and due to the low ceilings, we were having to fly at times as low as 100 feet, flying in between light poles on highways, flying over power lines.
The day always started pretty early. You would have our morning meetings to figure out what we're going to do that day, where we're going to try to get to.
United States Coast Guard, anyone out here?
And then we were out on the water the rest of the day, wading through water that was chest high. And we stayed out till 7, 8 o'clock at night, dry off, and go to bed for the night to get up and do it again the next day.
This was a high-risk operation. They are saving lives in the middle of tropical storm force winds and torrential downpours.
Our main mission was to protect the asset. We left the pier and anchored out in the Houston Ship Channel, dropping both of our anchors and two 12,000-pound sinkers over each side of the buoy port on our ship.
We were taking upwards of 1,000 calls per hour. There were more than 26,000 calls received.
What we would end up doing is going out, picking up as many folks as we could, until by policy they were no longer allowed to even keep flying. So people were really pushing their limits. But one thing I'll never forget is looking back in between hoists and seeing young children as young, sometimes as 5 or 6 years old, or even babies, getting hoisted up in baskets, and looking back and see our flight mechanics and rescue swimmers taking care of them and comforting them when they were in a really terrifying situation.
More than 100 Coast Guard families lost their homes to the floodwaters or to the winds, but every one of those responders there had their family back home and operated through the uncertainty. It's an amazing sacrifice for our crews to be fully engaged in a rescue operation, even while they're wondering about their families back home.
I was born and raised in South Texas, so I'm not far from home, and while the other buoy tenders coming from D8 and D7 that came in to help us work on our aids navigation, that gave us time to check in with our families and our houses to make sure everything was okay. So it was definitely something that I'm not going to forget about.
There was a young mother who had attempted to drive away from her flooded neighborhood, but became trapped in her car and had to climb on top of her car with her baby. We were able to launch an asset out there to go get her. So that one has stayed with me and will stay with me forever.
Our shallow water rescue craft assisted or saved close to 10,000 people. But when you think about the number of rescues that they directed, our junior petty officers in these boats would move into a flooded neighborhood, and because the boat said U.S. Coast Guard on the side, they were in charge. Local responders, state responders, Cajun Navy responders would come to our people and say, tell us what to do. Our petty officers would establish search grids, they would establish landing zones, and they would lead teams into flooded neighborhoods. And in that way, those junior Coast Guards, men and women, directed the rescue of probably 50 or 60,000 individuals.
The reason I joined the Coast Guard was to help people. And it just made me really proud to be a member of a service that goes out to help people first. And that is our highest priority.
We're talking about the Coast Guard heroes of Harvey, and there are many of them, and they're across our organization. They include our active duty, our reservists, our auxiliaries, our civilian employees. But there is the Coast Guard Foundation that helps the heroes, and I will tell you the foundation was in my office in New Orleans even while the storm raged in Houston, asking how they can assist Coast Guard families impacted by the storm. That provides peace of mind that allows our Coast Guard crews to do the work that they do.
So I have to say, Commander Leonard was part of that team, and so I'm very glad he was. We were at least able to see that ready acknowledgement of the work that they did during Harvey. And also, I'd mentioned that picture of the houses that looked as if they were along the canals. You saw it in that video, and I think you see it again here in the picture on the bottom right. Bottom left side here. So again, memories of Hurricane Harvey. And I believe there was actually another video. These pictures, of course, all showing aspects of the activities that they went through back during that period. But I think there is another video at the end, in which case we will run that as well. One thing I noticed that as part of their training, they included certified energy managers alongside emergency managers. And so we see, certified emergency managers, yes. Similar to energy managers, but emergency managers in this case.
When Harvey formed in the Gulf of Mexico, Coast Guard crews worked around the clock to ensure the safety of our people, assets, and facilities, to direct actions in order to minimize the risk to commercial ports, and to prepare for the search and rescue missions that we knew were to come. Even before Harvey made landfall in South Texas, Coast Guard air crews rescued a dozen mariners from the motor vessel Gulf Justice as she was aground and foundering in high winds and heavy seas at the leading edge of the storm. Harvey raged on for the next 5 days, and Coast Guard crews in aircraft and shallow water boats battled tropical storm winds and near zero visibility in a treacherous urban environment to rescue stranded victims, many of whom suffered from serious medical conditions and needed immediate treatment. And while our Coast Guard crews directly affected the rescue of more than 11,000 people in that time period, using our facilities, our command and control capability, and the on-scene initiative that defines our enlisted workforce, Coast Guard men and women directed and facilitated the rescue of tens of thousands. Even before the storm cleared Texas, our crews were on the water, working with partner agencies to restore critical channels and aids to navigation, and to ensure the port facilities were able to safely receive ships and start operations here in the Port of Houston and throughout Texas. Those efforts ensured that the area refineries not severely damaged by the storm were able to receive feedback and continue to operate. In the weeks and months following the storm, Coast Guard women and men responded to more than 670 pollution sites and removed over 58,000 gallons of oil and more than 8,500 pounds of hazardous material that were spread through coastal Texas by the storm and the floods. As the commander responsible for Coast Guard operations in a 26-state region, including all of Texas, I'm tremendously proud of what our Coast Guard men and women accomplished in the face of this historic storm, even while many of them suffered damage to their own homes and properties alongside their fellow Texans. Mr. Chairman, members of the committee, the men and women of the 8th Coast Guard District are proud and privileged to be members of the world's greatest Coast Guard, and we appreciate your continued strong support of our service. We continue to stand with Texas alongside Texans, ready for whatever comes next.
I just want to thank all 4 witnesses and who you represent, and everybody in the room who is a part of the response and recovery effort for your service to not only this nation, but to this great state of Texas.
All right, and yes, we certainly acknowledge the great work that was done by all the emergency responders during Harvey. One thing that I did discuss with Joe in preparation for this session was the aspect that a lot of what they did during that period was not simply to rescue people, but also to help restore the infrastructure of the whole region. And I mentioned earlier that disruptions to infrastructure often lead to delays in startups or long periods of running with disrupted supply chains. And that was an important part of the recovery from Harvey as well. Had it not been for all the work done to restore and resuscitate, if you like, the infrastructure around the area, there would have been much worse impact on supply chains and therefore a much worse impact on production and energy intensity within the industrial sector. Let's just go to the end of these slides quickly. And so I think a lot also of Commander Leonard's message was the can-do attitude that enabled the Coast Guard and the other emergency responders to get things done. Okay, at this point, we'll pause just briefly for some more Q&A. I had a couple of other questions come in. One person asked about surge capacity as an aspect of plant design. Obviously, if you add surge capacity, it generally means you need to make larger vessels within your plant. So there is a cost when it comes to the design of a plant in order to add more surge capacity. What the surge capacity does is to give you an opportunity to smooth out flows going into and out of equipment. And that benefits not only the stability of the actual flow rates, but it can also stabilize compositions, because if you have a certain amount of contaminated material or out of specification material, as in that distillation example I gave you, and you have a large surge drum, it may well be that even though a certain amount of off-spec material goes into the drum, by the time everything is mixed inside the drum, you may still be on specification. And so that's the benefit. And the result of that is that you may well be able to avoid a lot of reprocessing of material or discarding of specification materials that would be very expensive. Now, this particular example came from Charles Herzog, and he had some specific examples, but his basic premise was that generally just one off-spec material can pay for the additional cost of the increased size of your surge drums. There was another question that came from someone asking about research in the resilience area. There is a lot of research going on in electrical resilience, and maybe Kenny, you may have some comments on this during your session, Kenny. But certainly I know of a lot of work going on in academia on this, and there is some that I do know of to a limited extent within industry as well. In the chemical engineering area, which I'm more familiar with too, dynamic simulations also enable you to do a lot of evaluations of resiliency and the impact of, for example, surge capacity and how that can help you. And yes, the other question that came with that, will we be uploading the recording? And yes, the answer is yes. Look for it on the Texas Industrial Energy Efficiency Program website, hopefully within the next few days. All right, I think we need to move on. Kenny, I believe you are available now for your talk. So let me unmute you. Okay, Kenny, you're available now to give your talk, and I can advance these slides for you.
Okay, great. Can you hear me fine? Just want to test.
Yes, you're coming through loud and clear.
Excellent. Okay, well, welcome. It's a pleasure to be here. I'm honored to be a speaker. I originally had intended to speak out on the site and be physically present. And of course, we've since had this coronavirus pandemic, which is now resulting in all of us being together in a remote, distant environment. So it's a pleasure to see over 100 people online. It's kind of neat. It's really a cool way to have a conversation with you all. I like being in presence. I don't like to be separate, but I'll do my very best today to share some information. And you saw the slide deck from the Admiral, which was very impressive, his video around Hurricane Harvey. And I'm going to spend a little bit of time talking about the electric grid that serves the greater Houston area and how the resiliency of our grid has enabled us to ride through the big event called Hurricane Harvey. I also led Hurricane Ike back in '08. And so we've been through 2 once-in-a-100-year type events in 10 years. And then most recent, now we're in this pandemic event, which is probably just as big an impact in our economy and in our businesses as hurricanes have been in the past. So these all bring different dimensions of recovery and resiliency. And so hopefully I can share a little bit of our experiences in this brief talk with you all this afternoon. So if you'll move to the next slide, I'll try to allow you to handle the screen, and we'll move through this as we can.
Just one quick thing, Kenny. I don't know if you're able to adjust your camera. If you can, we're just seeing the top of your head at the moment.
Yeah, I wish I knew how to do that.
Okay, no problem. Yeah.
I can try. Nope.
Don't worry about it.
It is what it is. It's where it grows over time. So, okay, we'll go ahead and move on over to another slide.
Sure.
We'll get into the introduction right here. So just real briefly, who is CenterPoint Energy? We are a regulated utility, electric utility and a gas utility. Pretty large footprint. Everything in the blue area is how we are regulated. Most of this geographical areas are in the gas business. We're a gas distribution company serving close to 5 million gas customers in 8 states. I am responsible for the Red Star area for the electric utility. We serve the greater Houston area. It's a gigantic infrastructure that serves close to 19,000 megawatts of electric load in the summer peak. And it's about 26% or so of the total load in the state of Texas, which is managed by ERCOT. And I have been on the board of ERCOT for the last 4 years and very familiar with the ERCOT competitive market and our role to serve the Texas market. We're a small service territory with a gigantic load. We serve 2.5 million electric customers. What I do is I own the infrastructure. I no longer have the supply or the retail, but I own the delivery. And we are responsible for delivering electricity to our customers, obviously 24/7 in a very reliable fashion. And so today we're going to stay focused on the electric utility and how we serve the electric utility in the greater Houston area. So next slide. Okay, we're going to start with the video. I think you saw the 2 videos earlier. This is a very short video that gives you just a high-level summary of the impact of Hurricane Harvey to our utility just 3 years ago. Go ahead.
CenterPoint Energy, always there.
Thank you for showing that video. And I always enjoy that video. It's very short, very brief, but the purpose behind that video is while we own the power lines that deliver electricity from other parts of Texas into the greater Houston region, what's really most important about our company is we are a group of employees who are very experienced, well-trained. We work safely We're dedicated, we're very loyal. We live in the communities that we serve, and we take ownership, we take pride, and you see it in those faces. Our employees are, they're boots on the ground. They are essential employees dedicated to the infrastructure that serves the greater Houston area. All of the loads, the big industrial loads, all the big commercial loads, our residential loads, we serve them all, and we do it with great pride. And so we're always ready. This slide here just kind of shows you our preparation. We prepare every year. We prepare for the worst case hurricane, Category 5. We always set our minds around being prepared for worst case. If we're prepared for the worst case, we can handle every case. When you look at a case like Hurricane Harvey, we have smaller versions of Hurricane Harvey, every year, smaller events where we're well trained and well prepared. We use every event, thunderstorm related, flood related. We use every event as a lesson, as an opportunity to learn more about our processes, our technology, and our people. And so throughout the year, we prepare ourselves for the big event, but day in and day out, we're working on the smaller activities that we have to respond to. We're trained in incident command, just as you saw from the United States Coast Guard. Our employees are trained in the same language, the same processes, the same reporting. We want to be consistent and integrated with our governmental officials. When we train each year, we do a test about in May of every year in preparation for hurricane season. But we're already going through that right now. We're in a high activity alert right now with the pandemic, and we're well prepared. We're in this, what we call emergency operation planning right now as we go through the event for the coronavirus. And so we're as prepared today as we ever are. And as we go through our preparations, we also communicate with our neighboring utilities. When we get a big event, we depend on one another. We go help our other utilities, and they help us. And so we're constantly in contact with one another, and we're ready. We're always ready to prepare a response when called upon based on Mother Nature. So I'm going to move on to the next slide, but just to highlight the importance of our preparations throughout the year. So when we go back in time and we look at Hurricane Harvey, a record-breaking storm, these are just some of the highlights, big picture of the event. As you heard earlier, it came and went, it came and went, it came by and then it went, and it was a slow-moving, high-impact event storm. While the 130-mile-an-hour winds did not affect the greater Houston area like Hurricane Ike, it did affect the Corpus Christi area and areas just south of Houston. So the wind was a big deal, but more of a big deal in our area was the rain. Depending on where you were, where your customer load is, anywhere from 45 to 55 inches of rain what were recorded for Hurricane Harvey. And so the rain, it tested our creeks, it tested our bayous, it tested our rivers. And trust me, we know inside out where our creeks are, we know inside out where our rivers are, we know inside out where our bayous are. We understand how they affect our models and how they affect our operations in real time. This event had just a tremendous amount of lightning. Lightning creates outages in our service territory. And so we have to respond to the real-time impacts associated with lightning. And that's part of what we did with Hurricane Harvey. If you remember Harvey, it started on a Thursday evening into a Friday, and it rained all day Thursday, all day Friday. It rained all day Saturday. It rained all day Sunday. It rained all day Monday. I remember the first sunshine on a Tuesday afternoon outside of our emergency operations center, and that sun didn't last real long, but we had a little celebration at that point in time as we saw, the goodness of the after effects of Hurricane Harvey. So that was a positive outcome. Let's move to the next slide. Just showing you a couple pictures. Just you saw in the earlier videos, we have tons and tons of pictures. These are taken by our technology, and you can see that this is a transmission right away, and you see just a couple pictures here of how much water was affecting our industrial complexes across Baytown. We serve all of Baytown, all the way to Trinity Bay. And then lastly here, this is one of our staging sites, and this is an important picture because in a major event, we bring in mutual assistance crews. These are not my crews. These are other utilities, our neighbors. We live for one another. We We help one another, and what they do is they run their own armies, and they are well organized. They're safely trained, and we just prepare them to come into our service territory, what to expect, and then give them work. We give them material, we give them work, we give them hotels, we give them transportation, we give them food, and we try to give them some happiness. We try to make them feel comfortable being in our service area. We call them guests. We try to treat them like guests. And so this is 1 out of 6 staging sites. This Reed Road is just south of NRG. It's a couple, maybe about 10 miles off of 288 Reed Road. It's one of our critical staging sites that we use every storm event. Next slide. So just to put this in perspective, we've been working hard for many years on our intelligent grid. It started many, many years ago, back in 2006, 2007, 2008. We've made strategic investments in smart metering, one of the first utilities in America to put in the smart metering technology. We put in an advanced distribution management system so we could use that metering data and manage our grid in real time with real-time situational analytics. We've built an intelligent grid that allows us to remotely manage and restore power without the work of our linemen, so it reduces time and allows them to be more efficient and focused on where the trouble really occurs. And then we added a customer vision system that allows us to communicate to our customers in real time. When situations occur, we can then translate those situations into a message that's meaningful to our customers, which is very, very valuable to you and to us. And so you can see just some analytical information in here. The hurricane created an opportunity for us to use our intelligent grid. We were able to save minutes, 41 million outage minutes remotely through the management of our transmission and distribution system. So that what that meant is over 100,000, 140,000 customers got their power back on without any real field work, which is very important to us. Secondly, we were able to read our meters. In the old days, we would use our physical drive out and read meters manually. You couldn't do that with Hurricane Harvey because the roads were flooded. Well, now all of our meters are telemetered in real time. We can read our meters in real time. We were able to transact to the market. We were able to connect meters, disconnect meters, do everything we would normally do. We did it in real time, even during an event as big as Hurricane Harvey. So from a metering management perspective, it really had minimal impact to our competitive market, which is a very, very big deal. And then lastly, we are using real-time analytics. I'll touch a little bit more about this in a minute, which aided us in our operations around where was our trouble, where do we need to move our crews, how do we restore service in a much more efficient and safe manner to enable decision-making in real time to really improve our performance and improve our output. Next slide. So the impact of grid modernization, this is a theme that we as a utility have been committed to for over 10 years now. Hurricane Harvey brought a new dimension of technology, which is drones. Think of this 3 years ago when the drone was more of a science project or a tool for our children to play with in the backyards. We were able to get access to some very sophisticated drones back in that day and use them. We hired third parties who are much better at using them than ourselves. And we put them out on our streets, and they gave us situational awareness that we could not get on our own. It brought real-time status of damages to our hub and allowed us to make faster decisions on the work that needed to be completed that could be done in the office and then shipped back out through mobile data, as you see in here. And our crews were mobilely being managed through our mobile data systems, which basically enabled the technology to lead us, to really provide great visibility and great operational capabilities. And it made our crews much more efficient in real time. In addition to that, you see on the third bullet here, we have a system that we use today. It's called Power Alert. It's a Power Alert system that over 1 million of our customers a day, when their power goes out, we know it because the meter sends us a signal in real time. We can send that message to our customer in real time, and we can tell you today that your power is out without you even being at home, and we do that to you in a page or in a digital communication on your cell phone. We use that technology to keep our communities informed, to keep them aware of our situations, to give them better understanding of what we're doing and where we're going, and it provided a great tool for communications. I point out Memorial Sub. This was a big deal. I don't have any of the pictures here, but that's the parking lot. We have mobile subs. So think of our service area as 250 substations that are very important to providing reliable infrastructure to serve our 2.5 million customers. When the Memorial substation out in the Memorial area went underwater for the first time in 50 years, we were able to bring in a mobile sub and hook it up with temporary transmission, temporary distribution, get all those customers back in power within 3 to 4 days, and keep the sub operating until we rebuilt the substation over several months. So just a good example of how we were able to work in real time. Next slide. So I'm going to give you just some fast facts, just some fun facts about the storm. I know it's been a few years and probably a while since people remember everything in here, but we have electrical distribution circuits. We lost probably 15% of our circuits during Hurricane Harvey. Hurricane Ike, we lost 90% of our circuits. Almost the entire service area was dark. Harvey was not quite as bad. The wind wasn't as bad in the Houston area. It was a flood event, not a wind event. We had 8 substations out of water and 9 substations that we couldn't access. So that was a big deal. We brought in 2,200 employees and had a mutual assistance support from 7 states. And the impact in terms of outages was equivalent to 2.5 to 3 years of just normal weather. So it was a big event. It cost enough outages that it was equal to about 2.5 years of normal reliability on our grid. So it was a big event. It was a complicated event, but our technology really made a big difference in helping us get through it. Next slide. Here's again a picture of the staging site that you saw earlier. 352,000 hours there, 85 crew spokespersons. We serve meals. We bring in third parties who feed our crews for breakfast, hot meal for breakfast, hot meal for dinner. We pack them lunches for the middle of the day, and then we send them all home in hotels. We wash their clothes every night. We're like a small city. We take care of health. We take care of wellness. We take care of happiness, and we try to serve them as guests to our cities because they are very important to our response. Next slide. 1.27 million customers were impacted by Harvey in some way. We had a lot of unique equipment on this thing. You can see that the boats, we use boats instead of trucks in a lot of areas. We use airboats, we use drones, we use amphibious vehicles. And since Harvey, we bought some even better equipment that allows us to work in flooded areas. So we're even better prepared today for these types of technologies than we were back in Hurricane Harvey. Next slide. So I'm going to spend just a minute talking about communications. Again, the most important part of how we perform is how we communicate. And social media was a new thing back in Hurricane Harvey, and we took advantage of it. We went all in, and we notified our customers through our Power Alert services. We notified customers through Facebook, through tweets, through our website. It was a big deal, and it worked extremely well. Now, today, people are much more familiar with social media, so all these things that we did well there, it's expected today. It's anticipated. We better deliver on the communication front. Next slide. And this was the response. It was really positive. We were very, very impressed and very pleased with the response that our customers gave us through our communications, through the hard work of our crews out in the field, through our connectivity, through our real-time communications with our folks, through technology and person-to-person. Great feedback, and really a very, very valuable opportunity to work with our customers. Next slide. So after the storm, I'm going to be real brief here because I'd like to give you all time for questions and get to our next speaker. But we've worked hard on strengthening our grid in 4 major areas. We'll go to the next slide. The first area is in transmission. Hardening is important to us. And when I say hardening, we want to be wind resilient. And we look at wind from the coast of Galveston all the way to Conroe to the north of our service territory. And we build our infrastructure to withstand the power of a Category 5 hurricane. It's really important to us. And in Hurricane Ike, we had 0 or very minimal damage to any of our newer infrastructure. And so it's been tested. We can't get a better test than a storm like Hurricane Ike. And we continue to work hard to replace older wooden pole structures with high wind resistant steel and concrete infrastructure with anti-cascading designs, anti-galloping designs, and modern transmission construction. Next slide. In substation, it's about protecting the sub. We build walls to control against floods. We build fences to control against physical threat, and we isolate the heavy oil-contained equipment from fire. As you can see, fires can create big problems, and so we are fire resistant the best we can. We're water resistant the best we can. We have surveillance to protect against physical, and we have all this information that comes back real time to our central control system. Next slide. Distribution, we look at the infrastructure we can't build everything the same, but we look at it from Galveston all the way to the northern ends of our service territory. We try to select strategically where we put our intelligent grid switches, how we think about hardening. We can't just put everything everywhere. We try to do it in a systematic way. We try to put as much infrastructure support and strength in our system as we can. And then on top of that, we layer visible data that allows us to see things in real time so that we can be highly responsive to Mother Nature. Next slide. A lot of our service area is feeding very important Texas Medical Center, downtown Houston, the airport. And so we want to protect that equipment uniquely to serve the medical center, to serve our airport, to serve a lot of our critical loads. So that's where the resiliency comes in, is how well we're able to meet the needs of our critical loads in a much closer format. Next slide. Redundancy, this picture you can see on the far right is a building. It's kind of hard to see. It's down out at Spring Branch. We built that building 4 years ago, and it has the same functionality as our central control center. This is a FERC NERC requirement, and if something happens to our transmission control center in real time, we can move all of our dispatch controllers to the secondary system and operate the entire grid with the same level of performance and the same level of functionality, and they work live. And so we constantly have that level of backup built into our grid today. So all of our substations can meter data in real time to both locations, and our systems are operated in real time at both locations. This is a very important part of our resiliency that works extremely well to monitor and watch and control our grid. Next slide. We have mobility. We have command centers now, so we don't need to work in offices. In fact, right now, sitting here today, I have 3,500 employees, almost 4,000 employees. Of course, they're all across the states. We have several thousand here in Houston that are working remotely because of the pandemic event. We can mobile manage our crews. We can mobile manage our office folks. We can move where we need to serve the needs of our customers and serve the needs of our outside customers that are utilities in our neighboring areas. Next slide. And then this is kind of, in wrapping it all up, this is just after action. We work very hard with our national and our state industries. We collaborate. We try to learn from one another. We're always trying to build ourselves and make ourselves better for the next event. Next slide. And that concludes the presentation, and we will take questions. And if you have anything else you'd like to talk to me about away from the meeting, more than happy to do that through email or through phone calls. Thank you for your time.
Excellent. Thank you so much, Kenny. Much appreciated. And I know in the talk that I gave, I talked about the need for a resilient infrastructure. So when we're dealing with industry, the ability of the infrastructure to respond quickly and to get things back up and running fast is clearly a key factor, not just for production, as I said, but also for energy efficiency. And I think what you told us is some great things that you guys did during Hurricane Harvey to make sure that that's indeed what happened. So thank you for that, and thanks for the talk. There are several questions I've received while you've been talking. First one, I'm assuming is going to be fairly straightforward for you and simply a definition. Several times in your talk there, you talked about SAIDI, and the question is, what is that?
Yeah, it's a reliability metrics. It's the industry standard, and it basically means for the average customer in the industry, there's about 100 minutes per year of outage time. And that's about the average in our industry. If you're in an area where you don't have trees and you don't have lightning like San Diego, California, your average will be much lower than that. If you're in an area where you're in a jungle and you have a lot of lightning and you have a lot of things like Houston, Texas, then your average reliability will be different. But it's a centralized metric that for reliability purposes that we can standardly report on in terms of the performance of our grid based on the average customer and the average outage minutes per customer.
Okay, great. I'll come back. There's a second part to that question, but I'll jump ahead to the next one that I have here. You mentioned that 8 or 9 substations were inoperable due to being underwater during Harvey. First part of the question, have these substations since been elevated to harden from subsequent heavy flooding events? Well, just leave it there. Again, this question's got a second part, which I'll come back to in a minute if we have time.
Yeah, and the answer is yes. These substations are located very close to our bayous, and consequently, we recognize the threat. And what we have done, and I gave you that one example out at Memorial, we kept that mobile substation energized for months, and we re-energized the new substation. What we've done is we not mobily, but we physically lift all of the control equipment, all the control gear that is digitally sensitive to water, and we've elevated it above the 15-foot plane that occurred in this event, and even higher than that. So we've built a higher stage for future, which we think is very, very fundamentally important. And we're taking that same template, that same idea across all of our other substations and making sure that we have that longer term capability to withstand rising water in an event as big as Harvey.
I guess that leads into the second part of the question, which says, what are Centerpoint's lessons learned from Harvey? It sounds like there's one right there. Anything else you'd like to highlight?
Yeah, I think it's really the technology. We are a technology-centric world today, and we need to test it. We need to keep testing it. We need to learn how well it takes the pounding of testing, the physical pounding of our natural environments. And so we have discovered over the course of Hurricane Ike and Hurricane Harvey that our technology is solid, it's strong, it's resilient, it's robust, and it provides us a leading advantage in being able to restore services much more efficiently and much safer today than we ever could have done if you go back 10, 15, 20, or 30 years.
Okay, very good. And one more question here. What wind speed are transmission line and overhead power lines able to withstand? And what about microbursts and hurricanes?
Yeah, that's a good question. We've actually had microbursts. Microburst occurred. I was watching an Nationals game back in April 3 or 4 years ago, and I got a call at 8 p.m. that out in Sealy, Texas, we had a microburst. If you understand what that is, it's the opposite of a tornado. And it comes down, and instead of sucking everything in, it pushes everything out, and it literally just pushed this trail of wind and damaged everything in its route, and it went back up into the atmosphere. And so we had hundreds of poles down. We had damaged transmission, and we went to work in a Walmart parking lot. We took all of our mobile equipment out there, and then within about 24 hours, 48 hours max, we're back to normal in that event. There's nothing that can withstand a tornadic event of a major magnitude, just because of the unique damages that creates. However, our transmission system is built to withstand hurricane 150 mile an hour winds and was well tested during Ike. Ike was 110, but what was unique about Ike, 110 mile an hour wind, is it stayed for 12 hours. And so imagine, you're sitting there and you're taking that pounding for 10 hours. So it's 110 mile an hour wind, but it's for 10 hours. So it was a significant thrust and a significant impact. And our systems withstood we're very proud that it withstood the effects of that big event. Now, when you bring it down to distribution, where you have smaller poles, they're too close to trees. And so it's not how well does the wood poles handle in the wind, it's how much damage do the trees cause our infrastructure. We had trees falling over because of the heaviness of the trees, the big oak trees and the wind, and they would fall into our power lines, which takes a lot of work to restore services. And so the biggest challenge we ever have, I saw that in one of the questions, is big trees causing damages to our infrastructure.
Yeah, and in fact, that was the last question that I had on the list here. And so it did say, what was the biggest challenge for Centerpoint during Harvey and how was it handled? So beyond dealing with trees, is there anything else you want to talk about?
It's just really the quickness of evaluating your system. You have to do a full evaluation of your system, and you got to collect that data, and you got to bring that data back in. And then you got to go restore your emergency services. And so there's a time lag before you really can start helping your customers. And the more that we can reduce that lag to get your critical loads back on faster, get your data in quicker, is the biggest challenge we always have. And then being able to convert that into productive crews who can do the bigger work to restore larger amounts of power. That's our biggest responsibility.
Very good. Thank you so much, Kenny. Appreciate that great talk.
You are welcome.
And with that, I would like to move on to our final speaker, who is Chris Knoop. And I just want to check, Chris, you are there?
I am here.
Very good. If you would like to request control, if you are going to be advancing your own slides, while I just give you a short introduction here. So Chris is joining us, as I mentioned. He was the designated dinner speaker for the STS AICHE dinner, which was supposed to be taking place today. So his topic is not identical to what we've been talking about with resilience and lessons learned from Harvey, but I do believe what he has to say is something that will be of interest to everyone on the call, anyone involved in energy management and greenhouse gas emissions especially. So Chris is CEO of Carbon Sequestration, Inc., and also an active partner with timber management groups and timber owners in the American South, with an interest in reducing global CO2 levels. He's also a lawyer, so for those of us who are engineers, don't be too scared. I've talked to him and he's a nice guy. He has oil and gas experience, including energy contract litigation work, and he is owner of the Knoop law firm and president of Bankers Oil Corporation. He has a JD from South Texas College of Law and a BA from the University of Texas at Austin. And so, Chris, without further ado, I'll hand over to you.
Thank you, Alan, and thank you, members of the AICHE. Special shout out to Tom Rame, an AICHE fellow and also the founding member of the local climate solutions community. And we look forward to working with him later this year. One thing about me, I'm, as Alan said, I'm an attorney, and I'm very invested in the oil and gas side of things. So when people find out that I'm doing carbon sequestration, they don't know how to respond. They might think that I'm somehow adverse to the oil and gas industry and that I'm now an environmental proponent. But at the end of the day, what I've stumbled across is a potential new industry for Houston, Texas, and for this country. And it's something that the former president of Shell, John Hofmeister, has been speaking about since the mid-2000s. And also Lee Raymond, the CEO, former CEO of Exxon, which is that as an industry, if we are going to treat CO2 emissions as pollution, we need a price on that CO2 so that we can continue our profit-making activities. And in the past year, essentially, a price on carbon has started to emerge. And I'll get into that in a little bit. But again, thank you for your time listening to me. And I will try to tie this into Hurricane Harvey at the end. All right, let's get started.
Something went wrong there.
Alan, can you help me here?
Yes, we somehow went back to the beginning. So let me, I may just have to go out of sharing for the moment. So, all right, just give me a moment to recover the slides. And perhaps it'll be easier if I just take the control from here. There's obviously, the system gets a bit complicated when you start doing more than the basics. So lesson learned, we'll get through this. So let me go back here.
Well, I'd like to, while Alan is working on that, say a few things of why Houston is a great place for this new industry. And we've become very effective with the shale revolution at taking carbon out of the ground. And it would make sense that the specialists that take it out of the ground are the ones that pioneer getting it back into the ground.
Okay, you ready to move forward?
Okay, so let's get started. Professor Ning Zhang has been very generous with his time, talking with me about these ideas. He is the inventor of a sequestration technique, which is taking wood and burying it. It's as simple as it gets. And you can see from the diagram here that Professor Zhang, who is the chair, University of Maryland, Department of Atmospheric and Oceanic Science. The idea by Professor Zhang is simply to manage forests more actively. All the chemical engineers here, or some of you probably know the composition of trees and biomass. And until recently, I didn't. Trees are, from my understanding, mostly air. And the dense wood is approximately 50% carbon. So going back to the periodic table, the carbon weighs 14 and the two oxygen weigh 16. And so the conversion of carbon, or the degradation of carbon into CO2, results in a molecular weight of 3.667 times the original carbon molecule. So when we have carbon created through photosynthesis in dry wood material, and we let it degrade back into the air, evaporate essentially. If we took a different approach of managing that material, we could use the photosynthesis as a primary means of sequestration.
Want to move on?
Yes, next, please. Okay, the carbon cycle, real quickly, for those of you that don't know, the annual global uptake, or the amount of photosynthesis plus other sequestration of CO2 from the atmosphere, is about 220 billion tons. And fossil fuels, for example, only emit 36 billion tons annually into the atmosphere. So the world is very easily able to take the emissions from fossil fuels. The problem is the natural emissions globally. The largest emitter of CO2 is the world itself, and dead and dying biomass. So our largest emitter is biomass. We should also look at ways, if we're going to work on reducing emissions through fossil fuels, we should also look at forest management techniques to reduce emissions, natural emissions. You can see from the figure on the right, here in Houston, we're uniquely geographically located next to what I call America's carbon sucking asset, being the American South, with millions of acres of timber farms.
To move on.
Next slide, please.
Yeah, by the way, one comment, if you can try to speak a little louder or perhaps get a little closer to your mic there.
Okay, thank you, Alan. Is this better?
Good. Yep, yeah, that's strong. Good, thanks.
Okay, and this is from Professor Zhang's research on the matter. You can see the lifetime of buried wood is much longer than the lifetime of CO2 in the atmosphere. CO2 does stay in the atmosphere for thousands of years, but the majority of it will sink into the ocean or otherwise float down into the natural sinks, carbon sinks of the earth within a few hundred years. So buried wood is one way that we can bridge the gap towards a time when CO2 levels are lower. On the right, you can see that so recently, this is from our Facebook site, a tree was unearthed in New Zealand and carbon dated to be about 45,000 years old. And the condition of the wood doesn't look great, but you can see that it's still wood. Next slide, please. Another example of sequestration of wood is the existence of Venice. Venice is built on wood beams that are in an anaerobic condition, and therefore there is essentially no emissions. And so the wood in the Venice case is replaced by the lagoon minerals that are floating around, and you know, this is long-term sequestration for that wood. Another example is some wood found at an old harbor in Boston, and they are actually repurposing this 300- and 400-year-old wood. So wood burial is something that we do accidentally. Nature does it. And the question then is whether we can do this on a commercial scale with the new carbon pricing that we have available in an economic way. Next slide, please. There are three potential sources or large industrial sources of wood and biomass. And these are, number one, when forest is clear cut for timber, there is approximately 15 to 20% that is left over. They call this slash. And this slash, the production rate is about 15 to 20 tons per acre. So our first place that we're going to look is slash. There are two other areas where we can find wood products as a result of at the sawmill. And the third one would be end-use products, old chairs, old wood, down Allen Street after Hurricane Harvey. And all of these different species of woods are going to have different issues that we're going to have to deal with, but they are all potential sequestration components. Next slide, please. As to the slash that I mentioned, when timberland is clear cut, basically the sawmills are unable to take a tree that has less than a certain diameter. And with the recent timber prices really collapsing due to the COVID-19 situation, the sawmills are taking less and less of what is the unmerchantable tip. So all the limbs are cut off, the tip is cut off, and that's generally strewn back to the property and used as a type of mulch. We believe that we can use this mulch and bury it, taking advantage of the new carbon pricing. Next slide, please. In our case, we've chosen 2 locations to begin in East Texas, in the heart of the Texas timber industry. We're partners with American Forest Management, who's the largest forest management company in the U.S. Next slide, please. There are widely known data points from the Department of Agriculture on how much biomass is created and how much slash is created. This slide is simply to show how, that these slash numbers are well known. And most estimates are around 5 to 20 tons of essentially slash per acre. Next slide, please. You can see from this slide that there is a correlation between the diameter of a tree and its weight, generally on a species by species basis. And the species of tree that we're looking at is the Pinus taeta, the pine, loblolly pine tree. These are very fast growing trees. A DBH, or diameter at breast height, of about 12 inches gets you close to 1 ton of green weight. And then the conversion from green wet weight to CO2 is you cut it in half. So if you have a 10-pound branch in your yard that's newly cut off of an oak tree, about 50% of that branch is going to be water. About 50% of the remainder of that will be carbon. And using the 3.667 carbon to CO2 connection, we come up with about 91%. So if you have a 10-pound branch in your yard that's freshly cut, that's about 9.1 pounds of CO2. So I think when you start thinking about it that way, you see that we have the potential to scale this idea in a lot of areas of our life. Next slide, please. Focusing in on this 12 to 14 inch DBH because, and I'll show you from some of the other slides that the trees get to about this size when they're harvested, so they're growing fastest until they get to the 12 to 14, and then the time for it to grow larger than that is usually not worth it for a few different reasons. But the density of planting these loblolly pine trees, usually around 700 to 800 per acre, and a good forest manager will hope that 300 of those will survive per acre. 300 trees with a 12 to 14 DBH, each one weighing or having approximately 1 ton of carbon. So you can see from 1 acre of land, you would have 300 tons of CO2. So how long does it take to get 300 tons of CO2? Next slide, please. This slide is simply to show that the moisture content is a big part of the calculations, and it changes based on the weather and the time of the year. Next slide, please. Here we talk about pulpwood prices, and one of the really interesting things about the market right now, which is a little bit in free fall, is that pulpwood prices, which is wood used for generally for paper construction and other bags, cardboard, etc. The market is already, with the current carbon pricing, could be pricing out pulpwood. In other words, it could make more sense to use pulpwood or compete with the existing industries that use pulpwood and simply bury or sequester the pulpwood. Next slide, please. Here we see, this is from the U.S. Department of Agriculture. We see a chart which shows how many tons of carbon per hectare, which is approximately, I think, 2.47 acres in a hectare. But you can see, and then if we do our conversions here, this is a very conservative, these are conservative numbers, but you can see that the growth rate is pretty strong up until year 25, and then it levels out for an average stand. So you can calculate how much carbon you're growing, how much your standing stock of carbon is. Now, after about year 40, the forest is really, the DBHs are still increasing, but the amount of carbon being sequestered is less economic than it is at year 15 or 20, which is one of the things I think should be debated or understood a little bit better, and there's some new research coming out on this. We all love our forests, and we love the ecosystems that our forests provide. But one thing that we need to study and understand is that very old forests are like old folks' home for trees. And these trees might have plenty of wildlife, but they become net emitters of methane and CO2. A new study by the University of Delaware shows that methane emissions from tree trunks can be substantial. And methane, of course, is 25 times stronger than CO2 as a greenhouse gas. So, whereas the Kyoto Accords sets aside certain land for permanent forests, a permanent forest is not a sequesterer of carbon. A permanent forest is essentially a standing stock of the maximum amount of carbon that can be grown, and then becomes a net emitter of methane and CO2. So what could we do to manage these forests? Well, we could take out the old trees and bury them and let the new trees grow up. Already a lot of carbon management is being done in the Midwest with regards to the organic content of the soils using no-till processes. Next slide, please. Okay, to answer the question I brought up a few minutes ago, which is how long does it take a loblolly pine tree to get to a 12-inch DBH? And the answer is about 21 years. And you can look, there's various studies done on this. But so 20 years, if we planted 700 trees per acre, and then we're left with 300 or 400 good ones, that would be approximately 400 tons of CO2 per acre over essentially a 20-year time period. And as far as I know, this does not account for fertilization. So doing the numbers, 20 years to create 400 tons means that we could do, or we can essentially create a carbon stock of 20 tons per year per acre. That's substantial, considering that the average American emits 16 tons of carbon dioxide per year. So 1 acre can offset, if managed properly, 1 acre can offset 1 U.S. citizen. And we have approximately 325 million U.S. citizens and 1.75 billion acres available in both farming and timber land. So it is theoretically possible that through effective management of our land, the country could become carbon neutral or carbon negative simply by using photosynthesis. Next slide, please. This is a study done by a different professor, Zhang, not Zing, and this shows a control group of fertilized, I think 9-year-old pine trees versus non-fertilized. And you can see the lower figure showing the volume. It looks like approximately 25%, maybe 30% increase in volume, and I believe that there's a close correlation between volume and weight. So that number of 20 tons per year, we might have some upside to that if we're able to use fertilizer. Next slide, please. All right, assessing the carbon market, and right now it's a hodgepodge of different governmental organizations. There is a voluntary market where private companies and several of our leading oil and gas companies want to offset their operations emissions, not the content of the actual oil or gas that they're finding, but the operations that they conduct. They want to be carbon neutral. And on this voluntary market, carbon dioxide is going at around $12 per metric ton. The carbon markets are in some cases stackable. The new 45Q credit that's available through the IRS is $32.50. So whereas this method that I'm talking about may have not been economic at $12, it is now, with the stackable 45Q credit, if you can use it, very profitable. Generally, timber operations cost around $14 per ton. There's some upside to this pricing through some of the initiatives that are being used in California, such as the low carbon fuel standard, which essentially forces the retail drivers of and buyers of gasoline to make the gasoline or carbon neutral, or to some extent carbon neutral. Next slide, please. I think this gets into how do we get carbon credits? It's always the same. Carbon credits have to pass what I call triple MRV. The methodology has to be approved. The measurement has to be consistent. The monitoring must be ongoing and consistent with the methodology. There must be reporting to the correct agencies, and then there is independent verification. Almost the ACR, the American Carbon Registry, uses this triple MRV as well as the EPA. So our plan is to work with all of those agencies to develop triple MRV, and Professor Zhang is also helping us with that. Next slide, please.
And I should mention, Chris, we're pretty much at the end of our time, so we're pretty much at the end here, right?
Okay. Yeah, we are at the end, and I think we can open it up to any questions. I guess tying it back in with Hurricane Harvey, there is an opportunity to, in times of these hurricanes that knock out thousands of acres of dead wood, to bury that wood. That would be a perfect opportunity for for example, the fires that occurred off of Highway 71 a few years ago, to take that burnt and emitting wood that is emitting lots of methane and turning that into a net sequestration. I have a couple of chat questions here. One of them is, how deep must the wood be buried? And that is actually, that's the pit design. This slide right here, this was done by our KDW, a construction company here in Houston that's partnering with us on designing these pits. And this is called our mega pit. So in this case, it's actually a big hill, and we have a clay cap. These pits can only be constructed in areas where the clays meet certain requirements, and that's the job of our soil engineer. But essentially, the requirement is always the same. You have to have a secure geological state. And we also have designed what's a gas collection system, which is pipes that go into the reservoir of the wood and create low pressure areas that take out the methane. So, so are there any other questions? How deep must it be buried? I think that's an economics question. Professor Zhang wanted a deeper burial. I think the economics are pushing us towards more shallow burial. Another question regarding the problem of permanent forests. Can we encourage timber harvesting with burying / via carbon pricing? And I think the answer to that is yes. I know there's some other people in California that are trying to do this. Mr. Hoffmeister was talking about a person that wanted to take over the California Department of Forests and actively manage those forests, but ran into considerable pushback from Greenpeace and some other environmental groups. So I think once carbon pricing, as it increases, and the numbers that I showed you on that prior slide of $32.50 are going up to $70 by 2040 or 2045. So what is barely profitable now is going to be extremely profitable as we go forward. But the idea is to use photosynthesis and to pick the lowest hanging fruit when utilizing this new carbon market.
Very good. Thanks so much, Chris. We are out of time. There are several other questions coming in about other emissions associated with this and questions about pricing. But at this point, we do have to stop because we have past 5 o'clock, which was our end time. Did just want to just briefly here, we've got your contact information if anyone is interested in getting back and perhaps dealing with you more specifically on some of these things.
Yeah, I'm more than happy to speak with anybody. You can follow us on Facebook. We've got a website here, or feel free to shoot me an email.
Very good. Thank you so much, Chris. And so with that, I would thank you for joining our webinar. I should also mention that on May 7th, which should be a Thursday, we are scheduled for our water forum. Now, this also is scheduled to co-locate with the AICHE dinner meeting. I think nothing has officially been decided on whether there will be an in-person meeting or not. Most likely, given current circumstances, it will be a no, in which case we will have the water forum as a webinar as well. So either way, though, we look forward to seeing you on May 7th for our water forum. And with that, I bring this session to a close, and thank you once again for joining us.